All right, so we're going to continue our discussion of Lewis electron dot diagrams by taking a look at the 6 examples that you were asked to work on following watching the introductory videos on Lewis dot diagrams yesterday. And so we'll take a look at those 6, go over them briefly. Feel free to pause and rewind and go back over a section if you need to, but compare those to your efforts, your Lewis diagrams that you hopefully came up with. And hopefully you'll see that they match up pretty well. If not, please make note of where you had some discrepancies or what questions you have, what you don't understand, because you will have an opportunity in class to bring those questions up and we can look at those specific examples. The more specific your questions are, the more specifically I can focus on that and help you to understand where things went astray. After we go over that, then we will take a look at some guided examples of how we do Lewis diagrams for polyatomic ions, which we've been talking about and introducing and you're getting familiar with your flashcards. And then we'll take a look at some special examples where we have elements or molecules where the central atom may be able to kind of violate that octet rule. Where we can have either less than 8 electrons, hypovalent or electron deficient, or hypervalent central atoms where you have more than 8 valence electrons in that, or on that central atom. And then we'll take a look at situations where we have multiple bonds in our molecular structures. And this will revisit something that Professor Dave introduced in the original video on Lewis diagrams, and that was sigma and pi bonds. And so we'll point those out. Right, so just a quick reminder, one of the basic skills we're going to need for drawing Lewis dot diagrams is determining how many valence electrons we have to distribute in these dot diagrams. And so 2 ways that we can determine the number of valence electrons that a given element or given atom within a formula is contributing is either write the electron configuration and determine what is the valence shell and then count up those electrons, or sometimes the quicker way is to use a shortcut where we use the group number on the periodic table that the element is found in. Usually that group number is up at the top of the periodic table, right above the column where your element is. And depending on the numbering system, if it's the Arabic numbering system 1 through 18, like you see here on the screenshot, it's basically the ones place of that group number. So group 1 elements, your alkali metals, hydrogen, they're going to have 1 valence electron. If you looked at your halogens, group 17, they would have 7 valence electrons. And the 2 other examples you see here, nitrogen and sulfur. Nitrogen is in group 15, and it's got 5 valence electrons. Sulfur is in group 16, and it has 6 valence electrons. So that's kind of a quick way to get that number that is going to be crucial for us as we draw these diagrams. And then when it comes to drawing your Lewis diagrams, the basic steps, and again, there's going to be some modifications here or there, but for the most part, the first thing you would do is arrange the atoms. Whichever element there's one of, typically it's going to be the first one appearing in the formula. Notable exception there would be hydrogen. Hydrogen's not going to be a central atom, but the element that there's only one of will typically be at the center, and then all the other ones will be arranged around it. Then you determine the total number of valence electrons. And for the 6 that you worked on yesterday, you wouldn't have needed to adjust as needed for ions, as it says here, but that will come into play today. Then it's time to divvy out all of those electrons. And the first place you distribute is to bond the central atom to all of the outer atoms. And so for each of those connections, you would use 2 electrons to form 1 bond. Remember, we use that like with a line is how that's typically shown. And in terms of what type of bond is that, it is a sigma type bond. Sigma bonds are always the first bonds to be formed between atoms. Then we distribute electrons as lone pairs, starting from the outside and then working your way inward. So you start with the outer atoms first in order to satisfy the valence shells of those atoms. Now, unless it's hydrogen, your outer atoms are going to need 8 electrons. Okay, hydrogen can't hold 8 valence electrons, so therefore the bonding electrons, those 2 electrons, are enough to satisfy it. But any other element other than hydrogen is going to require the 8 electrons. And then if after doing all that, you still have any remaining electrons, you stick them on the central atom as lone pairs. And sometimes you got to get a little creative with how you put them in, but you should put them in paired up. Don't put, one on each side, put them together, paired up. And then finally, double check for valence shell satisfaction on all atoms in the structure. The outer one should have been satisfied, during the process, but then the central atom, there are a few that we have to make sure, have a very specific number. And if they don't, then we've got to do some rearranging with the ones that we've already distributed. Okay, so taking a look at the 6 that you were asked to take a look at and try after having watched the introductory videos and the sample for NH3 for ammonia that was worked through in the previous video that you watched. Here we have dichloromethane, CH2Cl2. So the first thing is to arrange the atoms. As we look at the formula, we see there's only one carbon, and it's at the beginning of the formula, so that's a natural fit for being the central atom. The 2 hydrogens and the 2 chlorines are going to be positioned around that carbon, and usually we do it so that they are, the 4 sides. If you imagine a square around that central atom, you would have an element on each of those sides. Now, whether you arrange them symmetrically like I have here, or if you did, your 2 H's, on the left and the top, and then your Cl's on the right and the bottom, or some combination thereof, really does not matter, truly, okay? So we have arranged the atoms. Next, we need to total our valence electrons. So we go to the periodic table. Carbon has 4 valence electrons. Hydrogen's got 1, but there are 2 of them in the formula, so we have to double that. And then chlorine is a halogen, and that's got 7 valence electrons, but again, there are 2 of them, so we have to double that number for a grand total of 20 valence electrons. So that's how many we've got to deal with. So now, speaking of dealing, we're going to deal them out, so to speak. And the first place that we distribute them is to the bonds. And so we draw a line connecting the central atom to each of the outer atoms. Each line represents 2 electrons. So right there, we've used 8 out of our 20, which means we've got 12 left. So now we distribute to the outer atoms as lone pairs. Now again, hydrogen can only hold 2 valence electrons, and those bonding electrons take care of that. So the 2 hydrogens are all right, but the chlorine only has currently 2 electrons, the ones from the bonds. Okay, each of those chlorines is in the same situation. So each one needs 6 more electrons. And so if we put lone pairs, okay, 2 dots indicate a lone pair of electrons, and we do 3 of those pairs around each chlorine, that gives each chlorine an octet. And it also distributes the 12 remaining electrons that we've got. And so if we check for valence satisfaction, the hydrogens are okay with the 2 bonding electrons, our chlorines each have 8, and we check the central atom, carbon, has 2, 4, 6, 8, 4 bonds for a total of 8 electrons. All right, next one is water. H2O, here's an example. Hydrogen's the first element listed, but there's 2 of them, and oxygen there's only 1 of. Okay, so here it's the central atom is not the first element listed, but there is only 1 of them. Okay, and so the hydrogens will be placed somewhere outside of that. Again, if you go left and top or straight across or top and bottom, really doesn't matter. I've done them linearly here. And so valence electrons, hydrogen's got 1, but we've got 2 of them, so we have to double that. And then oxygen has 6 for a grand total of 8 valence electrons. Not too many to deal with here. The first place we distribute is to the bonds. So we connect our oxygen with our hydrogens, use a line for that. Each line is 2 electrons. So there we've used 4. And that means we have 4 valence electrons left to distribute. We start with the outside atoms, but the outside atoms are both hydrogens. They don't need any more electrons beyond the 2 that are connecting them to the oxygen. So that means we've got extra valence electrons left over, and extra valence electrons get placed on the central atom as lone pairs. And so we would put 2 lone pairs on that central oxygen. Checking valence satisfaction, the hydrogens are okay with the 2 from the bonds, and oxygen in the middle has 2, 4, 6, 8. It's got the 2 bonding pairs, and then it's got 2 lone pairs. 4 pairs total, grand total of 8. All right, PF3, phosphorus trifluoride. Okay, as we take a look at this, hopefully you can determine that phosphorus is going to be the central atom surrounded by 3 fluorines. Our valence electrons, phosphorus has 5, and fluorine being a halogen has 7. 3 of them means a grand total, we're going to have 26 valence electrons. First place to distribute is bonds. Then we take care of the outside atoms and their valence shell needs. Each of those fluorines is going to need 6 more electrons to fill the octet. And so between the bonding electrons, that took us down to 20. And now we've got 6 electrons rather on each of the fluorines. 6 times 3, that's 18. We've got 2 left over, 2 electrons. So those leftover electrons are going to go on the central atom of the phosphorus as a lone pair. And if we check the valence satisfaction, all the fluorines have 8, and our central atom, phosphorus, also has 8. So there's that looks pretty good. All right, CBr4, carbon tetrabromide. Okay, first atom is the one that there's only one of, and so carbon is our prime candidate to be the central atom. Put the bromines around it. Summing your valence electrons, we see that we've got 32 here. The first place we distribute is to the bonds. So we put a line in for each of those, and that represents 8 electrons distributed, which means we've got 24 left to distribute. Looking at our outside atoms, we see that they each are going to need 6. And so 6 times 4, there's your 24. So we've distributed all the electrons. There are no extras to put as a lone pair on the central atom, which is okay. But we do want to check the valence satisfaction. Each of the bromines has 8, so that's good. And when we look at carbon, we see that carbon has 4 bonds, each bond representing 2 electrons. So that's a total of 8. And in this case, carbon definitely needs to have 8. That's one of those elements that's kind of locked in. But everything checks out with this one. All right, and then SiCl4, silicon tetrachloride. Now, in this one, okay, silicon is going to be at the center, and chlorine would be surrounding that. Now, here I've gone and I'm just totaling up the valence electrons, and I did this because if you're feeling like there's some deja vu here, it's not deja vu, or maybe it is. I don't know how you want to think of it, but when we looked at CBr4, carbon had 4 valence electrons, and bromine had 7 valence electrons, and there were 4 of them. So there too, we got 32 valence electrons. So we've got the same formula with the same total number of valence electrons. So it stands to figure that our Lewis diagram is going to look very similar. Okay, and this shouldn't be a surprise to us. It may be initially too. You might be like, oh, well, that's kind of cool, or it's coincidental. But honestly, we could have predicted this just by looking at the nature of the elements. Silicon is in the same family as carbon. It's in the same column. And chlorine is in the same family as bromine. Okay, elements that are in the same family as one another behave similarly. So silicon, in terms of its bonding, is going to bond in a very similar fashion to the way that carbon does. And chlorine, being in the same family that bromine is, will form similar types of bonds as bromine does. So how carbon and bromine will bond together will mimic how silicon and chlorine will bond together. All right, so that can be very handy to notice those similarities, or when you see formulas that are like, oh, well, some of their cousin elements, if you will, were involved in a similar sort of setup that can translate into, predicting the structure. All right, and then finally, OCl2, oxygen is going to be our central atom, chlorine's on the outside. And so valence electrons, oxygen was 6, chlorine has 7 each, times 2 for a grand total of 20 valence electrons. First place we distribute is for the bonds, and that takes care of 4, so there's 16 remaining, and we focus on the outside atoms next. Each chlorine is going to need 6, so between both chlorines, that uses up 12, okay, which leaves us with 4 valence electrons extra, and so they're going to go on the central atom as lone pairs. Checking valence satisfaction, everything's got 8, so we're good there. Okay, so in those 6 examples, again, if you've got specific questions, ones that you attempted and they didn't quite match up, please make note of those and ask about those. We can take a look at these again, and if there's a specific part that you're not quite sure why the dots went where they did, or why the lines went where they did, or why we used what valence number we did, Those are the kinds of questions that you should bring up in class when we have that opportunity. All right, so continuing on in that same notebook page, now we're going to take a look at polyatomic ions. So remember, polyatomic ions, multiple atom groupings, usually covalently bonded together, that collectively have a charge. And we see that by here, the plus sign in the upper right quadrant. So ammonium NH4, it starts out the exact same way as we did before. You arrange your atoms, so nitrogen's going to be at the center, and then the 4 hydrogens surrounding it. Now, when we total our valence electrons, we have to take into account that charge, because remember, a charge indicates that you've either gained or lost electrons. And so with a positive charge, remember that electrons are negative. So if we've got a positive charge, that means we've actually lost negative electrons, in this case, just 1. So what we need to do here is we need to subtract 1. Basically, you do the opposite of what the sign of the charge is. If it's positive, you're going to subtract. If it's negative, you're going to add. And so 5 plus 4 times 1 minus 1 is going to give us a grand total of 8. And so when we distribute our 8 electrons, the first place we go is bonds, and we form 4 bonds. So right there, we've used up the 8. And there's no extras to put on the central atom as lone pairs. Checking valence satisfaction, everything's good, because remember, hydrogen only needs 2, so they're all satisfied, and nitrogen also has 8. But what we have to do is we have to indicate, right, what makes this a little different than the previous examples we looked at, we have to indicate that positive charge applies to the entire particle, all 5 atoms covalently bonded together. And the way that we do that is by putting squared brackets around the Lewis structure and then putting the charge outside of those brackets. All right, let's try this one. BF4 with a -1 charge. So boron's going to be at the center with 4 fluorines around it. Boron has 3 valence electrons. Fluorine's got 7 times 4. Now we have a -1 charge, which means we've got an extra electron because electrons are negatively charged. So we're going to add 1, and that's going to give us a grand total of 32 valence electrons. Distribute to the bonds first, that uses up 8, which leaves us with 24. Each fluorine is going to need 6 more valence electrons to fill the octet. And so that's going to use up our 24. And when we check for valence satisfaction, the fluorines are satisfied. Boron has 8, so it's satisfied. And the last thing to do then is to put brackets around that structure and to put the negative sign outside of that. All right, now to look at some examples where got some slight modifications from some of our expectations in terms of valence shell satisfaction. Aluminum tribromide, AlBr3. Okay, we're going to put aluminum at the center, 3 bromines around it. Valence electrons, aluminum has 3, bromine has 7, multiplied by 3 for a grand total of 24 valence electrons. Put in your bonds first, so that uses up 6, which means we've got 18 remaining. Satisfy the outside atoms first. Each bromine is going to need 6 more. So right there, we've used our 18 valence electrons, and there's none left over to put as a lone pair on aluminum. So when we go to check valence satisfaction, the outside atoms, they've got 8, they're fine, but aluminum only has 6. And we might think that that's going to be a problem, okay? But when you are talking about central atoms that come from group 2 or 3, so again, the second column and the third column, the boron family, if you will, and the beryllium family, okay, the alkaline earth metal family, those elements can get away with being what we call being electron deficient, or sometimes we might hear the term hypovalent, hypo meaning less than or beneath. And so elements like aluminum or boron or beryllium or magnesium, they can actually get away with having fewer than 8 electrons around them. Okay, so even though aluminum doesn't have an octet, that is an acceptable structure for aluminum. Okay. All right, what about the opposite? What if we have more than 8 electrons, such as in phosphorus pentafluoride? Well, phosphorus is going to be at the center. When you get more than 4 outer atoms, you got to get a little creative with fitting everything around. So you just do your best, but make sure that they are all connected directly to the central atom or have that access. Phosphorus has 5 valence electrons. Fluorine has 7 times 5 brings us to a whopping 40 valence electrons. Distribute them the same way, bonds first. So that uses up 10. So we're down to 30. And starting with your outside atoms, the fluorines are each going to need 6. And there are 5 of them. So there's your 30 electrons. None left over. So there's no lone pairs to go on phosphorus. Okay. And when we check for valence satisfaction, the fluorines all have 8. Now notice here, phosphorus has 5 bonds around it. And each bond is 2 electrons. So that means phosphorus actually has 10 electrons around it. Okay. Now, if your central atom is in period 3, so remember periods are rows, if it's in row 3 of the periodic table or lower, that's okay. It can get away with that. Because, and part of the reason for that is once you get into that third main energy level, period 3, that's when we can start to introduce the D sublevels. And sometimes D sublevel electrons do get involved in some of these more complex molecules in terms of the bonding. Okay, so period 3 or lower, they can have, they're still going to, 8 is still fine, but they can exceed that 8. So what that means is, if we get a central atom, say that's in period 2, like carbon or nitrogen or oxygen, those have to have exactly 8. And it's because of that that we get into what we call multiple bonds. So if we take a look at this one, okay, CS2, carbon disulfide. Carbon's going to be our center. Sulfur is going to be on the outside. Carbon has 4 valence electrons. Sulfur has 6. So we double that, gives us a grand total of 16. So we distribute to our bonds, okay, and that uses up 4, so there's 12 remaining. And when we satisfy the valence needs of the outer atoms, we're going to need 12 electrons. So there we've used all our valence electrons. And the sulfurs are satisfied, but that carbon in the center is not. It only has 4 valence electrons currently. And carbon being in period 2, okay, it must have 8 valence electrons. It is locked in on that number 8, no less, no more. Okay, so what we have to do, because we've distributed all the electrons, we can't just pull them out of thin air and stick a couple pairs on carbon just because we want to. What we have to do is repurpose, if you will, some of those lone pairs on the sulfurs. Okay, and remember, these are covalent bonds. Covalent means the electrons are being shared. So if something's being shared, both parties, both atoms, get to benefit from them. Okay, so if we take a pair from that one sulfur and bring it in between the carbon and the sulfur, now both carbon and sulfur get to take credit for those 2 electrons. So sulfur hasn't lost anything, but carbon has now gained 2 electrons, so its totals up to 6. We're not quite there yet, so we're going to have to do it again. And there's some other things that come into play to helping us determine, well, do we take from the other sulfur, or do we just take another lone pair from that sulfur that we took from originally? And that's a topic for another discussion. But for today, we're going to keep things symmetrical here. And we're going to shift a lone pair in from that other sulfur. So now what we've done effectively is between each carbon and sulfur, there are 4 electrons bonding them together. And so remember, 2 electrons makes a bond. So if you've got 2 sets of 2, that means you've got 2 bonds. And that's what you see here with the 2 parallel lines. That's what we call a double bond. Right now, remember the first bond formed between 2 atoms is a sigma bond. Any bond formed beyond that is what we call a pi bond, okay? And so here we've got 2 sigma bonds, okay? One between, carbon and sulfur on each side. And then again, for each of those matchups, you've also got a pi bond. So a double bond is made up of 1 sigma bond and 1 pi bond. All right, last example, and we're going to look at today. All right, HCN, hydrogen cyanide. So here, all 3 elements, there's only one of them. Remember, hydrogen's not going to be a center, so the next most likely candidate is carbon. So we put the hydrogen and the nitrogen outside of that. Valence electrons, hydrogen's got 1, carbon has 4, nitrogen has 5, for a grand total of 10 valence electrons. Distributing to our bonds first, so those would be sigma bonds that we're forming there. Each of them uses up 2 electrons, so that's 4 that have been used. We're down to 6. So check the outside atoms. Hydrogen doesn't need any more. Nitrogen is in need of 6 to satisfy its valence shell, so we're going to put them all on there. And once again, we're out of valence electrons, so there's no extras to put on the central atom as lone pairs. The hydrogen and the nitrogen are valence shell satisfied, but the carbon, once again, only has 4. So this structure will not work as written here. We still have to do some work to get carbon to its octet and valence shell satisfaction. So we take some of those lone pairs from nitrogen and we repurpose them to become shared pairs. And if we do it once, we can do it twice. Remember, nitrogen doesn't lose out anything here because it's a covalent bond. It still gets credit for both of those pairs, still has its 8, but now carbon has a total of 4 pairs of electrons, one bonding the carbon and the hydrogen together, but now 3 pairs bonding the carbon and the nitrogen. This is what we call a triple bond, okay? And a triple bond is made up of 1 sigma and 2 pi bonds. Okay. Any connection between atoms will always have a sigma bond. If there's additional bonds beyond that first one, they're all going to be pi bonds. Okay, so hopefully with the first 6 examples that we took a look at, you had some success there. If not, make sure you've got your questions drafted to ask. And then with these additional ones, these are just some additional things to think about as we draw these Lewis structures. All right, so in our next lesson, we will take a look at that last example, ozone, O3, and some special consideration that comes in with that, and something known as resonance structures. So thanks for watching. Feel free to rewind, pause, rewatch sections, and look forward to getting your questions. Have a good day.